Here are two more solutions to two more of your questions, or partial solutions to your questions. So you also asked for 72 and 76, both of the kind of conservation of energy complex example section. For 72, we have Spider-Man stopping a runaway train. So I'm imagining what this is like. We have a runaway train at the beginning, right? This is like the before snapshot. And the train has some large velocity. We'll just for now call it VI. Spider-Man somehow deploys a web, which we are supposed to assume acts like a spring. The deployed web over some distance of stretch, right? I'm like, I don't know, this is sort of what a web looks like to me, maybe, right? So starting here, totally kinetic energy, runaway train situation, Spider-Man deploys a web, and as the web stretches, this train comes to a stop. So V ending is 0. The effect of the web was to bring the train to a stop, and I'm imagining the web acting like a spring and using this to estimate the effective spring constant. So we are told that the starting velocity is equal to 60 kilometers per hour. Of course, that's not SI units, so I need to switch that to meters per second. 1,000 meters per kilometer and 3,600 seconds per hour gives me 16.67 meters per second. I totally had to calculate that before I started recording. Ending velocity is 0 meters per second. The spring stretched a few city blocks in quotation marks, and they tell us that that is equivalent to 500 meters, and that the train has a mass of 10 to the 4th kilograms. So I'm thinking at the start, or the before, I have a train with all kinetic energy, and at the after, the end, I have a train with 0 kinetic energy because its velocity is 0, but a whole bunch of spring potential energy because I now have this web stretched tight, having stopped the train. I'm ignoring any changes in gravitational potential energy because I'm going to assume this occurred over a horizontal surface since I'm not given any information about the height differences in the city blocks. So I'm going to say that starting kinetic energy should be equal to that ending spring potential energy. Half mvi squared is equal to half kx squared. And we are given the mass of the train. We have transformed the starting velocity of the train to be in meters per second. We have a wanted effective spring constant of the spider web, and we know that the web had to stretch 500 meters. So I think that sets you up for a solution, and I leave the rest to you. Of course, if you still have questions, you'll certainly ask me on Monday. Number 76 has an elevator cable breaking when a 925 kilogram elevator is 28.5 meters above the top of a huge spring. And someone's just knocked on my front door, so we'll come back to this in a moment. Well, that's good. It was my Nespresso coffee order, so I'll be set for my caffeine needs for the upcoming week. Let's get back to the problem. We have a 925 kilogram elevator that is 28.5 meters above the top of a huge spring at the bottom of the shaft. The cable breaks, so we're going to think that the elevator falls. So this is kind of my idea of it. I have this elevator that is at the start. Let's see, it breaks when the elevator is 28.5 meters above the top of a huge spring. So I'm thinking that the elevator is probably at rest when the cable breaks. I'm not sure if that's a reasonable assumption yet, but I'll reread the problem. And I have this spring at the bottom that is uncompressed at the start. So we're thinking VI is 0 maybe, and we are 28.5 meters above the top of the huge spring. So above the top of the uncompressed spring. Okay, so something like that. And then the elevator falls, it gains kinetic energy, it then encounters the spring, it compresses the spring, which brings it to a stop at the bottom. So here I have end, spring compressed, and the whole point will be to stop the elevator, so VF is 0 again. We're supposed to find the work done by gravity. We knew the K of the spring was 8 times 10 to the 4th newtons per meter. Okay, so we're supposed to find the work done by gravity on the elevator before it hits the spring, the speed of the elevator just before striking the spring, the amount the spring compresses, noting that the work is done by both the spring and the gravity, and pull of gravity. So it's complex because we don't know how far down the spring is compressed. We have this moment here where we know that the spring is not yet engaged. So we have a situation where we've had gravitational potential energy converted to kinetic energy, but we know that that kinetic energy is now going to be converted. Well, actually here we're still above the lowest point. So we know that kinetic energy and gravitational potential energy is going to be further converted into spring potential energy. So what we don't know is this, what shall we call it? H, maybe HS for spring height. So, though, having stated that, I could set my lowest point equal to y equals 0. This will be my point of y equals spring compression. This is 28.5 plus spring compression. So I have set levels. And at the end, I know that the velocity is 0, so kinetic energy is 0. And at the start, I'm going to assume velocity is 0, so kinetic energy is 0. All right, so I'm talking through what I think is happening. I'm sketching at least a little bit as I talk, and I'm trying to use the talking and sketching to sort out what I know about how this elevator is moving and what I know about the physics of the situation. Let's see, I wrote down the spring constant, 8 times 10 to the 4th newtons per meter. I haven't written down this elevator's mass, 925 kilograms. And now I'm going to look at the questions again. So for part A, find the work done by gravity on the elevator before it hits the spring. So A is pretty straightforward. Work done by gravity as the elevator drops 28.5 meters. So the work done by gravity is going to be equal to the force of gravity multiplied by the distance in the y direction that the object moves. Gravity is pulling down, the elevator is moving down, these are in the same direction. So the work done by gravity is positive. The pull of gravity on the elevator is mg, is the weight of the elevator, so 925 kilograms times 9.8 meters per second squared times the distance it drops, 28.5 meters. And so, once I wake my phone back up, I have a work done by gravity, which is equivalent to the transformation from gravitational potential to kinetic during that section of 258,352.5, I might as well just keep it all there, joules, right? Or Newton meters, either way it works. So then the speed of the elevator just before it strikes the spring. So again, I can sort of ignore the fact that it's going to encounter this spring and go lower. I can say that the work done by gravity, which is equal to the initial gravitational potential energy, has to equal the kinetic energy of the elevator before the spring. The spring has never been compressed during my transformation from starting gravitational potential energy to spring potential energy, so I'm basically ignoring it. I'm sort of chopping off the bottom of my problem. I'm saying H is 0, and I'm just managing conversion from gravitational potential energy to spring potential energy. Here we have 258,352.5 joules, which is equal to half times the mass of the elevator times the velocity of the elevator before it hits the spring squared. I'll let you find that velocity. For part C, now we want to know the amount the spring compresses, noting here that work is done by both the spring and gravity. So I need to really go back to my original diagram. I'll just do that like so. Now I'm considering the full motion of the elevator. So I want to really think about how the elevator is, what sort of energy the elevator has at the very top, and then how that energy gets transformed at the very bottom. So at the very top of the top, I have an elevator with a sum total of gravitational potential energy but I'm not just going to use the height of 28.5 meters. I'm going to include this additional compression of the spring. I'm considering the full motion of the elevator now. At the bottom, I have 0 gravitational potential energy if I consider 0 meters to be this completely compressed position. So I have no gravitational potential energy, and I have only spring potential energy because at both points I'm at rest. I start at rest and I end at rest. So I'm thinking the gravitational potential energy at the top gets transformed into spring potential energy at the bottom. I have a 925 kilogram elevator at 9.8 meters per second squared because we're on Earth. But since I'm now considering the gravitational potential energy at the top versus the spring potential energy at the bottom, I need to consider that 28.5 meters plus the additional compression that I'm calling H of the spring. And then that gravitational potential energy gets transformed into spring potential energy, where the spring compresses from its relaxed position a distance of H subscript S. I didn't write in K. K is 8 times 10 to the 4th. So this is solvable. It will be a quadratic equation, and I'm confident that you can do it. I'll see you on Monday, and I can answer more questions on Monday, but we do need to move on to momentum and its conservation.